Welcome to review lecture 1-2, charge. After doing this, you should be able to understand the electrical properties of the particles inside an atom, the electric charge quantization, in other words, charge is restricted to certain values, integer multiples of the elementary charge E. The charge of a particle can then be written as n times E, where n is a positive or negative integer, and E is the elementary charge. Now, as a reminder, these lecture slides and videos are provided as a courtesy to the students. They are not a substitute for doing your work. You can't just watch the videos, read the lecture slides. Now, in Benjamin Franklin's day, which is around the time 1776, about the time of the American Revolution, electric charge was assumed to be a weightless continuous fluid. Now, we still use this model today, and it's amazingly good at describing what happens when an electric current flows. And we will be using this model over and over again. Now, from a quantum mechanical standpoint, it's not strictly correct. Okay, now Ernest Rutherford in the early 20th century revealed the organization of matter and identified the charges of its constituents. The atoms consist of a nucleus, which has most of the mass, and the surrounding electrons, which take up most of the volume. The nucleus consists of two types of particles, neutrons and protons. The electric charge is a fundamental property of all normal matter. Now, nobody knows what dark matter is. If you're interested in that, take astronomy. I love to teach astronomy. Now, inside the atom itself, by convention, protons are positively charged, electrons are negatively charged, and neutrons are neutral. That means they have a charge of 0. Electrical forces arise from these particles in atoms. The protons in the nucleus attract the electrons and hold them in position near the nucleus. So the electrons are attracted to protons, but electrons repel each other, and protons also repel protons. How the heck does a nucleus hold together? Well, it turns out that the neutrons hold the nucleus together via the strong force. The strong force is much stronger than the Coulomb repulsive force between the protons. The fundamental electrical property to which the mutual attractions or repulsions between electrons and protons is attributed is called charge. So every atom has a positively charged nucleus surrounded by negatively charged electrons. All electrons are identical twins to all other electrons. The nucleus is composed of protons and neutrons, otherwise known as nucleons. All protons are identical twins to all other protons, and all neutrons are identical twins to other neutrons. Atoms usually have as many electrons as protons, so the atom has zero net charge. Proton has nearly 2,000 times the mass of an electron, but its positive charge is equal in magnitude to the negative charge of the electron. A neutron has slightly more mass than a proton, and if you look at this carefully, if you add the mass of the proton to that of the electron, you have very nearly the mass of a neutron. And neutrons can actually be made by squeezing electrons into protons. That's how neutron stars are made. Now, you might want to copy this table into your notes, because it could be handy for you to use later. It tells you the mass of all the different neutron, proton, electrons, and the symbols, and of course the charge on each one. The atom is held together by the attractive electrical force between the positive nucleus and the negative electrons. Electrons and protons have charges of opposite signs but exactly equal magnitude. At the atomic level, unit of charge is called the elementary charge, is represented by the symbol E. Now be very careful, don't get this confused with other times we use that same symbol. Unfortunately, we run out of letters to use for things like this. So this is the reason why you can't memorize your way through a course like this, because you'll get the symbols all confused. The symbols E negative and E positive are used for the electron and proton charge respectively. This is called the elementary charge. It has a magnitude of 1.602 times 10 to the minus 19th coulombs. Unit on that is the coulomb. We'll define that later. Now, a note on sig figs and things like that when you're doing calculations. You should always look at all the sig figs that are in your calculation. Carry all the digits till the end. Don't round off till the end. Round off at the end of the proper number of sig figs, and be very aware of those, because on tests and homework problems, those computers are extremely literal. If you don't get the sig figs right or you round off incorrectly, you might get the wrong answer. So if you do get the wrong answer, check your sig figs and units. That's usually where the mistake lies. The nucleus has a net positive charge and attracts 4 electrons. This has a positive charge of 4. It will attract 4 electrons. The electrons are captured and held in an atom's electron cloud in a stable configuration. Actually, each electron instantly assumes an orbital, that is an energy probability level, whose circumference is an integer number of electron wavelengths. Electrons do not assume other levels because this behavior is quantized. If they try to assume a level where the circumference is not an integer number of electron wavelengths, the wave dies out and the electron isn't there. It's someplace else. Okay, the atomic number Z of an atom represents the number of protons, that's the number of electrons in a neutral atom. which also determines the chemical properties of the atom. The mass number A, it's written like this, okay? Here's the atom itself. That would be its symbol on the periodic table. Here is the number of protons and neutrons together. That's the mass number within the atom. Okay, this is the generic notation. And this is the number of protons. That determines where it is on the periodic table and its chemical properties. So this one is generic notation. This one is uranium-238. That's an isotope of uranium. Has 92 electrons, 92 protons if it's neutral, has 238 nucleons. And if you subtract these two numbers, you'll end up with the number of neutrons in this particular isotope. So this would be the isotope uranium-238 or U-238. Other isotopes, here's an example of uranium-235. We have the same number of protons. That's the same Z here. So it's in the same place on the periodic table. And its neutral going to have the same number of electrons. It has a different number of neutrons. And that gives it a different A. Okay, it gives it a different atomic mass number. And this is uranium-235, another isotope of uranium. So the net charge Q net of an object that contains any electrons, NP protons, and NN neutrons is defined as Q net equals E minus times NE plus E plus times NP plus 0 times NN. And we can rewrite that. The 0 is going to cancel out as E, that's the elementary charge, times the quantity NP minus NE. Now we can rewrite this as little n times E, where little n is the number of protons minus the number of electrons, and all of these n's are integers. This net charge is quantized. It only can be integer multiples of the elementary charge E, where E is 1.602 times 10 to the minus 19 coulombs. So there's a principle of conservation of charge. Conservation of charge says that electrons, which are a fundamental particle, are neither created nor destroyed, but are simply transferred from one material to another. In every event, whether large scale or at the atomic and nuclear level, the principle of conservation of charge applies. In other words, the total charge you have in the beginning is the total charge you have at the end. Any object that is electrically charged has an excess or a deficiency of a whole number of electrons. Electrons cannot be divided into fractions of electrons. You don't have half an electron. A charge of an object is always an integer multiple of the charge of an electron, where the charge of an electron is 1.602 times 10 to the minus 19th coulombs. And this is E, which is the elementary or fundamental charge. Now, no exceptions to this have ever been found. So here's an example of a nuclear reaction. Uranium-238 will spontaneously decay into thorium-234 and a helium. So here is uranium. Uranium-238 has 92 protons, and therefore, if it's neutral, has 92 electrons. It will decay into a neutral thorium-234. Now we have 90 protons and 90 electrons, plus 1 helium. And that will have 2 protons and 2 electrons. Notice that the electrons and protons all add up. There's no creation or destruction of either one. And you end up with the same amount before and after. Now, when a massive star runs out of fuel, its core collapses so violently the electrons are squeezed into protons. This makes neutrons. Even here, charge is conserved. The electron has a negative E charge. The proton has a positive E charge. The neutron, you add these two together, you wind up with 0. By the way, this won't happen to the sun, which is not massive enough to suffer this fate. The sun will do some other nasty things as it gets older. Okay, now all normal matter is made up of atoms, and atoms are made up of equal and opposite charges. Electrons are negative and protons are positive. An object that has equal numbers of electrons or protons has no net electric charge, and we call that neutral. If there's an imbalance in the numbers, then the object is then electrically charged. Imbalance comes about by adding or removing charges. Typically, the protons are fixed in space, especially in solids, so they usually do not move except in plasmas. Electrons are more or less free to move, so they get added or subtracted during charge transfer processes. When the electrons are transferred by rubbing from the fur to the plastic object becomes negatively charged by a certain amount Q. The fur will become positively charged by an equal amount Q because the charge is conserved. Now, we talked about this before. Fundamental rule is that the base of all electrical phenomena is that like charges repel and opposite charges attract. But everywhere on the Earth and in most normal situations, everything is balanced. Now, this is a good thing because the electrical force is billions upon billions of times stronger than gravity. And since we are not stuck to everything around us, the attracting force and repelling forces cancel out. This is called electrical equilibrium or neutrality. So the electrical forces acting on you balance each other, that is, cancel and have no noticeable effect at all. This normal state of matter is neutral, where the charges balance and cancel, which is a good thing. If this were not true, the universe as we know it would not be possible, and we would not exist. An object that has an unequal number of electrons and protons is electrically charged. Electrons and protons have an opposite electrical charge. In neutral atoms, there are as many electrons as there are protons, so there's no net charge. An ion is an atom that has unequal amounts of protons and electrons. This atom is no longer neutral. Positive ions have lost at least one electron and have an excess of positive charge. That's in a typical solid. Negative ions have gained one or more electrons and have an excess of negative charge. A plasma is the fourth state of matter, solid, liquid, gas, and plasma, that occurs when the gas is heated until the electrons jump off the atoms and zoom around by themselves. Plasmas are composed of positive ions that its atoms stripped of one or more of their electrons, negative electrons, all zooming around with thermal agitation. Plasma is the most abundant state of normal matter. Stars are mostly made of plasma. Most everything you see in the night sky, except for the moon and planets, or a satellite, or a plane flying overhead, is made of plasma. If an ordinary candle flame is at least partially ionized, that's a plasma. So is an arc, lightning bolt is a plasma. Positive ions are missing electrons. They have more positive charge than negative charge. A negative ion has gained electrons and has more negative charge than positive charge. So ionization is the process of removing an electron from an electron cloud of an atom or adding an electron to it. There are several ways to do this. Okay, here's a positive ion. A positive ion, this one has lost one of its electrons. So it has an excess of positive charge and a deficit of negative charge, and we call that a positive ion. This negative ion has gained an electron. It's got an excess of negative charge and a deficit of positive charge, so it is a negative ion. And usually this is only temporary. This doesn't last very long because nobody likes to be either positive or negative. They want to be neutral. Now, molecular ions can be created when one or more of a bond in a large molecule is broken. So this is typically, here we have a large molecule and this is electrically neutral. And if you rub this, it will break one bond here. And this positive half, this little positive part, becomes a positive molecular ion. This negative part becomes a negative molecular ion. So this one, the positive side has lost an electron to the negative side, which has gained the electron. This is the way in which a plastic object is charged by rubbing with wool, or a comb is charged by passing through your hair. So this is how that's what happens inside the comb when you comb your hair on a cold winter day, dry winter day, and you see it pick up all the little particles and stuff like that, pieces of fuzz, or stick to your hair. Charge. The amount of it determines the strength of particles' electrical interaction with objects around it. Charge is usually represented by a little q or a big Q. It is a property of matter. Properties are that there are two types of electric charge. There are forces among charges. We call them by Coulomb forces, and we'll talk about Coulomb's law in a later lecture. Charge is quantized and charge is conserved. Thank you.